let's say I have my little yellow ball attached to the spring. Now I'm going to pull it down by a short distance and let go. Once I let go, the spring would oscillate up and down, and it might carry on for some time. But what happens after some time? What happens after a long time? We would expect friction, even air resistance, and we would expect the oscillation to slow down, the amplitude to decrease, and after some time it has to stop. Okay, so that's what we would expect for anything on Earth, basically, that moves. Everything that moves have to stop, including ourselves. Right. Okay. So let me represent this with a graph. Let's say this is the time axis, and that is the x-axis, where x is the displacement. So with time, after I release it, the graph would look like this. We go up and down, up and down. But after a time, we would expect the amplitude to get smaller and smaller and smaller, and eventually it will stop, or it will be just extremely small. So that's what we would expect. Now, this friction or resistance that causes a spring, or causes an oscillation to slow down, to decrease in amplitude, and eventually to stop. When this resistance, when we talk about this resistance in an oscillation, like for this spring, we normally use the term damping. Right. So damping is usually used to refer to resistance in an oscillation. The resistance in oscillation. Now, just suppose that I want to do an exercise, just hypothetical, just imaginary. Suppose I want to imagine that somehow I can adjust, I can change or increase the amount of damping on the string, or on this oscillating object, this moving yellow ball. Now, how can I say increase the oscillation? I can actually think of two simple ways to do it. One way is to take this spring and dip it in water, or just take a cup of water and push it up over the ball, so that the ball gets immersed in the water. Then there'll be plenty of water resistance, and the oscillating ball would surely come to a stop very quickly. Now another way, maybe a bit flimsy, is if I perhaps take a little piece of paper. I take a little piece of paper and stick it here. If I stick a little piece of paper there with a little glue, for example, then as this ball moves up and down, this little piece of paper would be moving up and down through the air, and because of its surface area, it would increase air resistance, and that would slow down that would slow down the motion. Okay. So suppose that I can somehow increase this oscillation. This damping, this resistance in oscillation, which is called damping. Suppose that I increase this damping by using a piece of paper. Then I can imagine that if I use a bigger piece of paper, there would be more damping. And as we have seen, the damping would cause the amplitude to decrease as it slows down and stops. So if there is more damping, it would decrease more rapidly. Okay. Now, now I'm going to redraw this in a way that's going to make it easier to see the effect, slightly easier to describe the effect of the damping. So I'm still going to attach my piece of paper there. Okay, and I want to think about the oscillation. So let's say I put it, I displace it by a certain amount so that when I release it, the time t is equal to 0. So I start at a certain displacement, and as time passes, it oscillates. All right, it oscillates. It goes up, down. But because of the resistance, the amplitude decreases, gets smaller and smaller, and eventually we would expect it to come to 0 so that the ball stops oscillating. Now let's imagine what happens if I use a bigger piece of paper. Okay, so that means more damping, more resistance, and so the amplitude would come down faster. So let me draw another graph over it to show that it comes down faster. So if it comes down faster, it means maybe something like this. Okay, so the amplitude here is smaller than before, here even smaller, and even smaller, even smaller. And you can see that the idea that it will decrease more quickly and come down to 0 more quickly. So that's what we might expect, right? If I have a bigger piece of paper. Now let's say I increase the piece of paper even more. I increase it so much so that what happens? So that as the when I displace it, when I pull it by a certain amount, that means when it's there at 0 time, when I do that and let go, all right, if it is possible to have so much damping, that means maybe such a big piece of paper that the resistance is so big that it prevents the, or as I let go the ball and the ball moves towards its rest position, the resistance might be so much that it prevents the ball from overshooting its rest position to the other side. Meaning that on the graph, as the graph falls back towards 0 displacement, it doesn't actually, there's so much damping that it can't overshoot the rest position anymore to give this up-down motion. Instead, what it might do is that if the piece of paper is so big, it will slowly move back towards the rest position. Okay, it will slowly move back towards the rest position, and it slowly come to a stop at the rest position. Okay, slowly come back to a stop. But there's just too much resistance for it to move fast enough to overshoot the rest position. So you're just it will just slowly get back to the rest position without oscillating. So this is another extreme. You can imagine that this is an extreme case when there is a lot of damping. So now, having seen these two extreme cases, we might imagine. Let me give some names to these two situations first. So this very extreme case, in which there is, that there is a lot of damping, and so much so that there's no oscillation at all. This and the spring and the ball comes back to the rest position quite slowly. We call this over damping or over damped. Right? We describe this by saying that this ball or spring is over damped. Now, whereas in the other case, where there is only a small amount of resistance or very little resistance, the ball can continue to go up and down for some time before the amplitude slowly decreases to zero. So in this other extreme case, when there's just a very small amount of damping, we describe this by saying that the ball or this system is under damped. So it can be over damped, too much damping, under damped, very little damping. Now, but what is also of interest is the in between, or the sort of the dividing line, if you like, between these two situations. Now, you see, underdamped means that it overshoots, right? So overdamped means that it doesn't overshoot, but it returns to the rest position quite slowly. Now, the in-between situation we might imagine is that there is just enough damping so that the ball doesn't overshoot, right? Just enough damping so that it doesn't overshoot. But because there is no more damping than that, so the ball would return to the rest position in the quickest time, in the shortest possible time. So let me draw that. So we might imagine a ball coming back towards the rest position in the shortest possible time. Alright, unlike the overdamped case where it takes a long time to come back, or even underdamped case, alright, which overshoots, but actually it takes a long time for it to stop. So this in-between case, alright, is like the dividing line between the overdamped case and underdamped case, is where it comes to a rest in the shortest possible time. And this case also has a name. It's said to be critically damped. So okay, so while we are here, let me also write out the other way we would use these terms. Now, as I've written it, overdamped, critically damped, and underdamped, these three terms we use as adjectives to describe this system, like an overdamped spring, or overdamped system, overdamped oscillation. But we also need a noun. We also need a noun to describe this condition, if you like. Now, the noun for that say for overdamped would be over damping. For critically damped would be critical damping. And you can guess what is the third one. For under damped, it will be under damping. Okay. Now, but okay, so fine. We can do that. We can stick a piece of paper there, increase the air resistance, and we can see all these effects. But so what? What's the point of all this? But this effect is actually very useful in everyday life, even though we don't actually see these uses in a very obvious way. And one common example that most of us would probably encounter every day, if you have ever sat in a car or a bus before, all right, is this problem about underdamping and overdamping. All right, it's the problem of the bus shaking every time it goes over a bump. So I'll talk about that in the next video.